So, good evening, everybody. My name is Dubsky, and today I would want to talk to you about the mid-stack inlining, which is quite a big change compared to the previous speaker because we will shift like 3/4 levels of abstraction lower to the area of compiler optimizations and low-level stuff. So before we start, what will we talk about? So first of all, we will talk about inlining. I can say that inlining is like optimization that basically optimizes function calls. So first of all, we want to talk about the motivation, why we actually do it. What does the function call actually cost us in Go, and why it makes sense to optimize it. Then we will take a look to standard inlining, the rules that apply to it. And at the end, we will talk about how can we use those properties and this knowledge to actually write faster low-level Go code. So the cost of a function call, like we all know that processor executes instructions one by one. And if we want to call function, the processor actually executes some call instruction, which executes the code somewhere else. But it's not just it. And there are many things that the compiler has to actually do before the function call and after that. This is already specific to Go. This is not in each language, but in Go, this is basically it. It might not be complete. Not all of the points might apply to all the function calls. We will get to that. So first of all, store and load callers registers. So when we have a function, our function uses the CPU registers to store some values, to calculate some other values, and so on. When we call another function, we basically need to store those values somewhere because the function we are calling will use those registers to calculate its own values. So before each function call, the compiler has to store most of the registers it has to the stack, to the coroutine stack. Then it calls the function. And then, of course, later, when it returns from the function, it needs to, again, load all those registers back so that it can proceed with the calculation. You can see it here in the Go assembler, where basically this is code taken from gRPC curl, from some random function call. I have even no clue which one. But in general, you can see that the compiler is moving the BX register to some place in the stack, then the CX register to some place in the stack, then the AX. Then it does some other preparations. We will talk about some of them, not all of them. Then it calls the function. And then when it returns, it again loads those registers from the stack. Of course, it doesn't apply to all the registers. If the compiler just concludes that it no longer needs the value, it doesn't have to store it. It doesn't have to load it. Feels obvious. Second thing is prepare arguments and read return values. So since some version of Go, I'm sorry, I don't remember which exactly, we have register calling convention in Go. So when you call a function, you actually pass your parameters to some registers, which are defined by the API. So they are for all the functions the same. The first parameter is always in the same register with some nuances. And when you call a function, the function knows that the first parameter is in this register, the second parameter is in this register. In the past, all the parameters and returns values were actually passed via the stack. In some version, we have register calling convention. So if all the values fit registers, they are actually in the registers. But the compiler still has to arrange those values, those registers. So it has to make sure that the first parameter is in the agreed first register and so on. And of course, then it has to take the return value and again, store it from the registers. Then we have the cost of the call itself. This is not Go property anymore. This is property of the CPU, where the CPU basically executes many instructions in parallel. Very simplified here. And most of it is trade secret of the manufacturers of the CPUs anyway. But it really likes when it can have many instructions in a row, and it can parallelize their execution, basically overlap many of them, and so on. In case when you go somewhere or make jump, it's the same case, or conditional jump, the CPU kind of doesn't like it that much because it needs to evaluate where you want to go, which code you want to execute, and it cannot execute anything in parallel with it. Here in the graph, I have just some random instructions, and basically the visualization is that the CPU executes many of them at once. Those are the orange ones, and it, of course, completes some of them, which are the green ones. But when you do something like a call instruction, the CPU actually has to conclude where you go, it has to fetch the new instructions, it needs to execute, and so on. So the function call actually takes a while when the CPU just cannot execute anything more. It cannot start anything more because it just doesn't know what to execute. So at the end, you will get there, but you lower the parallelization of the execution. Now we get to the place where you actually call the function, and those are a few first instructions in the function. Again, simplified a bit. As many of you probably know, in Go, we have like growing coroutine stacks. So basically the stack is unlimited. You never see any type of error that you are out of stack, of course, unless you are out of memory at all. So functions that actually need a stack have to check whether they have enough space in the stack free for their parameters. And if they don't, they need to allocate a bigger stack. And to implement this, the compiler generates those few instructions at the beginning of each function, where basically the first block is the check, which is executed unconditionally in every function that needs a stack. The code below is where the jump instruction jumps, actually. This is executed only in case you are out of stack or in case garbage collector wants to preempt you. So those three instructions unconditionally executed with every function call. And as you can see, the instruction actually loads like the reference is another piece of memory and so on. So it takes a while to execute. Then we have stack frame creation. When you have a stack, you basically have like variables of one function. And when you call a function, you create another stack frame on top of that, where the function stores its parameters. And in order to be able to effectively trace this back and trace where any error happened or generate a stack trace, you want to keep the base pointers. The base pointer, when you have the stack pointer points to the like last value in the stack, or the first unused value, depending on the architecture, doesn't matter. But the base pointer points to the very beginning of the function frame. So whenever you call a function, the compiler basically stores the previous base pointer, then says, my base pointer is now the beginning of the stack, the current place in the stack where I am. And then it allocates some place for its stack frame, which here is the sub instruction because the stack is growing from the bottom address to the top address. So it's not add, it's sub. And again, when you return from a function, you have to reverse this operation back so that the function that actually called you ends up in the same state where it was when it called you. This is, again, generated for each function that uses some stack. And now I'm not sure if for functions that do not use stack, probably yes, because you want to see them in the stack trace. And the last thing that we will see also later is that function calls limit some compiler optimizations. So when you imagine this code that just like floors the number to even number, you can, like, compiler sees it, is able to optimize it, is able to generate code for it. But what if you call it with something like this? Here, the compiler could actually conclude that the return value will be just 10. Like, it's obvious. But because there is the function call, the compiler actually doesn't see it with some stars again. So we will see another optimizations later, but long story short, the function call blocks some optimizations of the compiler and forces it to produce more generic code, which in general means slower code. So the problem we have is that all of the things we have seen are basically constant cost. Most of the operations we have seen was fixed number of instructions, with the exception of the limitation of optimizations. So in general, the cost of call instruction is quite high for small functions. When you have a function that executes only 3 instructions, you pay how many? 10, 20 other instructions just to execute those 3 instructions. So this, of course, doesn't work very well for short functions. And we still want them because we still want to have nice and clean code. So here comes function inlining. Function inlining is the compiler optimization that actually takes the body of a function you call and just copies it to the place where from you call it. Of course, you don't want to do this for the whole program, because if you have a big function that is called from 20 different places, you would grow your program code quite a lot just by inlining it. So the compiler wants to have some heuristics, which function makes sense to inline, which function do not make sense to inline. But long story short, for most of the short functions you write, some getters and so on, those are not actually called in the code. They are just inlined, and the code of your getter is actually in the code where from it is called. So, So in Go, the function inlining is performed on the abstract syntax tree. For those who do not know, when the compiler parses your code, like the code you write actually in the Go, it builds the abstract syntax tree that basically says like, there is a function and in it there are those instructions, or there is a for loop with those parameters and in it there are those instructions and so on. Those statements. Statement is better word than instruction. So on this representation, very early in the compiler, before it does most of its magic, it performs inlining. The decision which function to inline and which is already too complex is just heuristics. It cannot know actually, and it doesn't know. It just has to decide somehow. So it's some heuristics based on the complexity of the function, based on how long it looks, how long it feels it will execute. It decides whether to inline the function or not. And the consequence of this is that we can affect inlining by just writing shorter or longer functions, of course. But disclaimer, do not try to over-optimize this. The compiler typically knows very well why it has the heuristics set the way it has. So when we have some example, I have just 2 functions that check whether an integer is even. And the first one is just simple one-liner. The second one differs just by the Go no inline directive. So, this directive just tells the Go compiler, please do not inline this function. It actually prohibits inlining of the function. It's not much useful in production code. It's mostly for presentations and benchmarks. And then I have 3 benchmarks. I benchmark the even inline. I benchmark the even no inline. And I also decided to benchmark when code when I manually calculate whether the value is even or not. So here is no function call. Just one detail, the sync variable. The compiler is actually that smart that in this case it can conclude, well, you never use the value, so I do not have to calculate it. So the sync variable is just global variable where the compiler writes the value so that it is actually forced to calculate it, because otherwise I would be benchmarking just the for cycle. And when we take a look to the benchmarking results, you can see that the even no inline is way slower and the even inline and manual inline are just very comparable. Basically, this is not that the manual inline would be slower. This is just imprecision of the measurement. So you can clearly see that calling the function, setting the parameters, executing the call instruction itself has some cost. When we get to another example, and here I want to show you how the heuristics actually work. So in this case, I have the same even inline function as I had before, the simple one-liner. And then I have a function which, as you can see, the for cycle will never execute. It will be just never executed. The compiler will conclude that this will never happen, that the function call will never happen. So actually, when you check the assembly code generated, it's identical, absolutely identical for the function. But when you benchmark this, you actually find out that the even complex takes same time as the not inline function. Why? Because, as we said before, the compiler decides based on the complexity of the Go code that was actually written in the very early stage. So it doesn't know yet that the for cycle will never execute. It sees, yeah, there is some for cycle, there is some call in that function, in that for cycle, that will be probably expensive. I won't inline this. So yes, the inlining decision is based on non-optimized Go code. So basically on the code you write. And of course, the inlining works transitively, where the compiler tries to inline the bottommost functions in the call tree first. And then if the resulting function is still simple enough, it again inlines it. So when you check the code here, basically the even sum is very similar to the even inline. There is no call instruction. You can see that it never calls. It just executes all the instructions. And when we again benchmark this, we conclude, okay, the even sum is a little bit slower. It has more work to do, but it still is not that slow as the even no inline. So we can see there is definitely no function call happening, because otherwise we would have to pay for the function call and the time would be actually higher. And now we get to the mid-stack inlining. So all that we have been presenting so far is inlining of a leaf function, which means function which doesn't call any function. With the even sum, we had a function which was calling another function, but the function that was called was inline, so it effectively became leaf function and was inlined after that. Starting since Go 1.9, the compiler actually executed the non-leaf function inlining. Interesting fact, it wasn't enabled before, not because the compiler wouldn't be able to do this, but because the stack traces would miss the functions that were inlined. And there were necessary changes to make sure that the stack traces still contain the functions that were inlined, so that people do not get lost in the stack traces. Before Go 1.9, they were inlining the leaf functions for the cost of not having the leaf function in the stack trace, actually. So the mid-stack inlining uses the same inlining heuristics, basically, but applies to functions that actually call other functions. And as we have said, functions are inlined from the bottom. So basically, mid-stack inlining is applied to simple functions that call more complex functions, that call functions that were not worth inlining. And by inlining, we have said that by inlining, we can enable compiler some other optimizations. And that's basically the point of this presentation, what I want to talk about, that by carefully splitting our complex functions into simpler outer function that can be inlined and more complex inner function that will be actually called, we can gain some performance benefits. So I was able to find 2 use cases. I'm not sure this is exhaustive list, but this is all I could think about. So the first one is that we want to avoid the actual cost of the function call, that we want to avoid all those preparations and so on. An example of that might be the sync mutex lock rewrite, where basically, where this makes sense. This makes sense when we have like simple function that we call, it will get inlined always. When we have complex function, it will basically never get inlined. But when this makes sense is where we have a function that sometimes is simple and sometimes is complex. So we have some like easy path and hard path. In the mutex, when we imagine that, the mutex, when we lock the mutex and it's unlocked, we just say, now it's locked, and we are done. When we reach the mutex that is actually locked, we have to like block the routine. We have to enqueue it somewhere so that it's waken up when the routine that holds the mutex actually unlocks it, and so on. So this is quite complex operation compared to simply locking the mutex. And shortly after the mistake inlining was introduced, there was this patch in the standard library of Go. Basically, this, what I'm showing here, is the full change. There were some other changes to tracing because basically the authors of this patch didn't want to log slow function to be visible in stack traces, so there are some other changes. But this is the whole patch that make 14% speed up in case of mutexes that coroutines are not fighting for. And how they did it? They did exactly the separation to simple and hard path. So when you reach the unlocked mutex, you call the lock actually gets inline because it's very simple function. It performs one atomic operation, one check, and if the check is successful, you are done. And in case it was not the case, and unfortunately the mutex is locked, you conclude, okay, okay, it's night. You have to pay the call of the function call, but at this point, it's negligible compared to the cost of actually putting the routine to sleep and so on. By the way, the same patch arrived later for unlock, which made another 9%. I won't show it here because it's basically the same. When I unlock the mutex that nobody is waiting for, it's very simple. I just unlock it. When I unlock the mutex that somebody is waiting for, I have to iterate some list, I have to wake up the routine and so on. So you can probably imagine that. Another situation, the other situation when mid-stack inlining might make actual sense is when you want to avoid heap allocations. So for those who don't know, Go decides based on the code whether it has to allocate your struct or your array on stack or on the heap. And basically the rule is if Go can prove that you will be using the struct, the channel, the slice, the array only in a given function or in a functions you call from that function, it allocates the structure on the stack. If it cannot prove that the reference to this thing won't outlive the actual function, it has to allocate it on the heap. And as we know, heap allocations bring some costs. The heap has to be garbage collected and so on. So you want to allocate as much as possible on the stack, but the compiler has to be still able to prove that it is safe. All of us have probably seen some CVs around C software because of this. So that's what the code tries to avoid. So example of this, when you take a look to the elliptic curve package, the curve 25519, it uses exactly this technique. This is the actual code of the library, and it's very common that you will see this in crypto libraries or in hashing libraries. Basically, how this works, you have the outer function that just allocates the array you want to return as a slice, and then you have the complex function that actually calculates the point on the curve, which you can imagine is quite hard thing to do. It's quite a lot of code that I just wasn't able to fit to the slide, by the way. And when it returns the exact byte slice that was allocated, the exact array that was allocated before, and the compiler is able to deduce that this slice actually doesn't leave the stack, And yeah, by not having to allocate it on the heap, you won't get much of a, by the way, I just tried, I tried to benchmark this. I tried to benchmark this by just adding the go no inline directive to the exported function. When you see the comparison, it's not slower. The issue is that it allocates more. And with garbage collected languages, you pay the cost for the allocations later during the garbage collection. The allocation is actually very fast. The garbage collection is slow. And when you have some server that does this cryptography very often, of course, having to garbage collect more slows it down. So by this, you can lower the amount of allocations. Yeah, a few disclaimers at the end. First of all, you might have noticed that in this presentation, there was not a single interface. The reason for this is that compiler is not able to inline interface calls just because the interface can be arbitrary function. So the compiler cannot know, and it always has to be cautious. So it has to do the full calling convention as we present it. It cannot optimize anything and so on. Second, what we have been talking about are heuristics in the current Go version. They might change. Probably, it's very likely that Go won't make inlining worse. So in most of the cases, if something works in the current version, it should work in the following versions. But there might be still nuances to that. And last thing, please, if you ever try to do this, think multiple times whether you need this. Like, this is interesting part, interesting optimization. You can see it in crypto libraries where it actually makes pretty good sense. But most of the times, just having readable code is better. So thank you for your attention. And I am ready for some questions.
Questions? No questions.
One question, is there some way how to know if my function will be inlined or not?
Yeah, when you have the, I think it's GC flags parameter of the compiler. So you say go build dash GC flags dash -m, if I remember correctly, and it will tell you most of the optimization decisions it does. It has different verbosity levels. And based on the output, you can actually conclude like, okay, it concluded that this function should be inlined, this function is too big, it won't be inlined, and so on. I used this many times when I was preparing this presentation. So yes, and there is support for this in the standard compiler.
I have actually two questions. You said it's not possible to inline a function that uses interfaces. And at the same time, you showed in the beginning the magic command that forces the inlining. What will happen if I enforce the inlining for the function?
It wasn't forcing inlining, it was prohibiting that.
Sorry, so you cannot force it.
You cannot force it. The compiler is smart enough to decide on itself. And by the way, funny detail, in C++, you have the keyword inline that actually doesn't mean inline. It means compiler, please don't complain when you see this function multiple times and do what you think is the best.
Okay, then I have only one question.
It looks like probably I missed the point, but according to your benchmark at the beginning, looks like the inline function actually faster than non-function at all. Was that correct? Or?
It was very identical, and it was like,
a little bit faster, yeah?
It looked a little bit faster, but it's like imprecision of the measurement. We are measuring like fractions of nanoseconds, so.
Yeah, I see, okay.
I still like had browser in my laptop and so on. I was listening to music, so it can vary.
So have you tried GCC? Does it produce a different result because it has clever heuristics based on other code?
I haven't. My assumption was that most of the people just use the standard Go compiler, so I decided not to make this specific to something else. And let's be honest, I didn't have time. I prepared this presentation yesterday.
Some other questions? If not, thanks, Jan. That was